Welcome to our NPTEL lectures on advanced power electronics and control. Today we will continue with the space vector modulation, but it is applied for the multi-level inverter. Let us see that we have discussed for the 2-level inverter how this concept can be extended to the 3-level inverter. We shall revisit the diode-clamped inverter again, but purpose here to discuss the diode-clamped inverter is something else. We will be discussing 3-level inverter and its space vector modulation. For this purpose we require to little actually recap. For this reason I decided to again speak about the diode-clamped inverter. So, as you know that basically these are actually it is a 3-level inverter, diode-clamped inverter. So, it has been realized by the 4 switches and switch pairs actually SA1 and SA minus and SA2 and SA2 minus receives the inverted gate signals. So, this switch and this switch are inverted in actually will have the inverted logic, and this A2 and A2 prime will have a inverted logic. So, for this reason one of the 4 binary combination SA1 and SA2 1 0 is not used, since it does not provide any current path to flow to the load. So, you have to remember that there are few actually states which cannot be incorporated in the diode-clamped inverter, and all the switching devices in the 3-level NPC needed to block half of the receiver's voltage that we have discussed already in our diode-clamped inverter. Now, you know that actually the different mode of operations, once you get this voltage VDC, basically you will have this S1 and S2 are conducting, thus you get the total VDC, and when you want basically VDC to be conducted, again same way you want to get a 0 voltage, you can get this S2 and S3 as conducting, and similarly once you want to get the lower decibels voltage, it is minus VDC, then S3 and S4 should be conducting. See, actually you can say that this one is SA1 and then this one will be SA1 prime. So, S1 and S3 are the complementary logic, and S2 can be said to be SA2, similarly it can be said to be SA2 bar. So, this is the way we will be synonymously choose the represent. When we say I actually will prefer this kind of notation for sake of simplicity, we shall actually correlate. SA1 is S1 and SA2 is S2 and SA3 is actually SA1 prime and S4 is SA2 prime. Now, this is the logic. Now, we will implement the space vector modulation. The space vector modulation for the 3-level NPC will be explained here and can be extended to the any level NPC. So, and students required to actually understand it, and question can be given for the higher level NPCs also. Hence, the operation of this inverter phase leg can be represented by different way of notation. Different book follows a different notation. For this we try to incorporate all the notations, so that student does not get confused in a different kind of notation is I have actually put into the different kind of books. So, basically switching state P, O and N, that is actually some books also write one actually basically one is when it is a 2-level phase vector modulation, we are happy to do with the 0 and 1, but when it is a 3-level, generally actually we have to choose basically this one, or we sometimes write plus 0 minus, either of these notations will be used. So, where actually minus VDC stands for N, 0 stands for O and the positive VDC stands for P. Some authors represents, that is what it is, that is basically that is what I was representing, minus 0 plus or 0 1 2. Now, let us see that how many states are possible. Taking all the 3 phase into the account, inverter has a total count of 3 to the power 3, that means 27 possible combinations of the switching logics will be possible, but there are redundancies and there are some actually states which cannot be incorporated, taking the logic that S1 and S3 are the complementary and S2 and S4 are the complementary. And for n level switches, the NPC will be actually n to the power 3. So, if it is actually 5 level, it will be 5 to the power 3 combination switching states will be there. For these 3 level NPCs, among 27 states, there are 8 redundant states, and so we will have a 19 basically the position vector available. Let us see those. And to find relationship between the switching states and their corresponding space voltage across, there is some procedure used for the 2 level inverters. So, that procedure will be extended, this concept will be extended to the 3 level inverter. Based on their magnitude, the voltage vector can be divided into the 4 groups. One is actually the 0 vectors, because we know that actually in the 2 level inverter either 1 1 1 or 0 0 0 was the actually the 0 vector, but that is basically the where will be represented by this O or 0 0 0 or n n n minus 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 for the magnitude of the 0 vectors. There will be a small vectors, that is V1 to V6. We shall show that all the vector will have a magnitude of VDC by 3. Generally actually all the vectors of the 2 level inverter has a magnitude of the, if you follow the Benhu's book, it is actually 2 by 3 VDC. So, it will be half vector for the system or small vectors. Each small vectors has 2 switching states, one containing P and the other containing N, and therefore, can be further be classified actually P minus P type or the N times small vectors. And medium vectors, basically these are the medium vector, it is for, we will name them to 7 to 12, those magnitude basically actually VDC by 3, and the large vector will have a magnitude basically 2 VDC by 3. So, this is the 3 level diode-clamped inverter, and these are the different vectors. O, so it is a 0 vector. Thereafter, you can have this state if you want to get it here. You have a combination to choose, there is a redundancy here, it is P00. That means this switch will be closed and here you have to manage. So, get PO. Again same state you can get here with the ONN. Similarly, but if you wish to generate basically this vector 13, basically what we have seen, please recall, basically 1 to 6 are the small vectors. So, 1 to 6 are the small vector. So, this vector is actually 1, this vector is 2, this vector is 3, this vector is 4, this vector is 5 and this vector is 6. And if you extend till this is 13, this is 14, this is 15, this is 16 and this is 17 and this is 18. And there are few vectors, this is basically vector V7, V8, these are half angle vector, angle is 30 degree. So, along this actually there are these numbers of vectors available and we have to generate the different switching state based on that. See, we require to do little bit of calculations, we can see that this vector is this sectors or it may be in this sector. Then what we require to do, we require to shift the origin and ultimately this may boils down to a actually the 2 level inverter. So, since it is here, since this vector is located, we have to find it out the actually the hexagon. Let us assume that it is available here instead of here. Then what we will choose? You will choose this rhombus and ultimately you will shift this origin. So, ultimately you have to add this vector basically V1 and thereafter you can think of this is actually made of now this vector we require to generate. Now, of course, you be sure that, so this is the actually the categorically it becomes again a 2 level inverter solution, and because you can see that here in this particular hexagon what are the switching state available to you. So, this is basically this is not a 3 level switching. In this hexagon it becomes basically a 2 level switching. Why? Because you see the state available to you. Here it is PNN, fine. So, it is positive and others closed. So, here it is basically there is a 1 bit change PON, and here it is PN0. Similarly, here actually you can get ON or POO. So, thus this vectors it boils down to actually a 2 level inverter, and ultimately because of this symmetric switching pattern. Students are required to go through the Benhu books, which is very well explained in that particular books. Now, we have to find the timing of this actually vector. So, we have taken this part of the vector that will be actually it will be there. So, see that we have this reference vector to be generated, and that is the that has been made by V0, V13, V1 and so on. Ultimately, you can understand that actually you have to make this vector by this. So, we require to calculate the time duration for the individual vector to generate this V reference. The dual time calculations for the NPC inverter is also based on volt second balancing method, as we have done for the 2 level inverters. The reference vector Vref can be synthesized by the nearest stationary vectors. These are the nearest stationary vectors, and for instance Vref falls in the region 2 of the sector 1. The nearest vector that will be actually used to actually fabricate these vectors are V1, V2 and V7. V1, V2 and the V7. So, this vector is V7. Now, let us see. So, we require to calculate the time for the each duration. So, this class it should be equal to V reference, and rest of the time should be given to the null vector, and TA, TB, TC equal to should be TS, and where TA, TB, TC are the dual time for the V1, V2 and V7 and V2 respectively. Now, you see that how you will calculate it. The voltage vector V1, V2, V7 and the reference figure can be actually shown there. Since actually this voltage V1 is a small vector, its magnitude is basically Vd by 3, and V2 is actually half vector, half angle vector, that is Vd by 3, it is 60 degree. Similarly, this is a half angle vector, this is actually V7, it is root 3 Vd by 3 e to the power 30 degree. So, for this reason, and this is your V reference, thus we can write this volt equation balancing. So, 1/3 Vd instead of V1, root 3 by 3 Vd, for we can split it into the axis in the cos and sine. So, thus it becomes this, and 1/3 Vd also cos and sine. And now you can see one thing, actually you can equate the real and imaginary part, that is actually real part and that is the imaginary part, and splitting the real imaginary part, what essentially you get this and imaginary part is this. Now, we require to solve these equations, another is Ta plus Tb plus Tc equal to Ts. Then from there actually you can get basically Ta equal to, now we have to substitute this is something like modulation index in the sine triangle PWM. So, that is root 3 by Vd. So, ultimately you substitute here. So, you get Ta equal to Ts 1 minus 2 m sin theta. Similarly, so this will be Tb will be this and Tc will be this. Okay. So, these are actually the expressions for Ta, Tb, Tc. Very simple expression, and you, since you know the theta, so of course you substitute and you know the magnitude of Vref by Vd. So, all those magnitude will be given and you can calculate all the timing required for you. So, this is all about to calculations of the NPC. The overall requirement of the switching sequence of designing NPC inverter are follows, just briefing out how we require to do that. The transition from the one switching state to the next switching involve only two switches in the same inverter leg. That is what we have actually, what we have done, we have actually, though it was a 3-level inverter, in a particular hexagon it behaves like a 2-level inverter. One leg being switched and other legs are switched off. Transition of VREF moving from one sector or the region in the next sector require no or minimum number of switching. So, that is something we require to be actually incorporated, and the effect of the switching states of the neutral point deviation required to be minimized. Based on this principle, we shall actually calculate the switching timing of the reference vectors for diode-clamped 3-level inverter, and of course, you can actually go for any level of inverter by same method. Now, let us see direct AC to AC converters. The AC to AC voltage converters operates on the AC mains, and we require to have it. Problem is that most of the cases actually we require AC to AC conversion. For example, we take an example like modern elevators and air conditionings. You got a compressor that is AC and you are feeding with the AC, but problem lies you require a variable frequency AC and variable voltage AC. So, but that cannot be actually achieved without the help of the power electronics. So, for this reason we can have a AC to AC regulators or converters. AC to AC voltage converter operates on the AC mains essentially to regulate the output voltage. Portion of the supply sinusoidal appear at the load, while the semiconductor switches block the remaining portion of it. So, essentially this is basically, we have seen this example like you may have a triad, that is essentially a simplest actually AC to AC converter, but it actually chops the portion of the voltages in both the direction and is applicable for the low power loads. And if you increase the power, then you can have a anti-parallel thyristors. Anti-parallel thyristors can actually generate essentially a AC to AC conversion. So, these are basically the different way of AC to AC conversion. And apart from that, you can have this combination also, that is a load, that is AC, and you can have a SCS. So, this S-share can be shorted or open depending on, you can convert AC to AC, that we will see later, these circuits and these circuits. So, this is an example of the AC to AC conversion of the single phase AC regulator operation with a resistive load. So, this is the applied voltage, and you have a thyristors is triggered at an instant here in a positive half cycle. So, you get actually the V load as a green portion of it and L load actually the red portion of it. Again you have trigger in a negative half cycle. So, this one is, this thyristors actually triggered, and thus you get the lower portion of it, and essentially thyristors blocking voltage is basically the pink one. So, what should be the RMS value of this voltage? You can integrate over it 1 by pi 0 to alpha v square sin omega t d omega t, and essentially this will be the actually the RMS voltage of this AC to AC conversion with dual thyristors. And so, the fundamental current IF can be represented by IF equal to under root 2 V by R pi. So, this is the actually the voltage. So, you have to divide it by R. So, you can get this value plus this value. So, this will be the current, and average power you have to multiply with this actually VL into IL. So, if you multiply, you will definitely will get V square by R pi minus alpha by 2 plus sin 2 alpha by 2. So, this will be the average power across this basically RMS power across this load. Now, if it is inductive load, then essentially what will happen, actually current will lag. So, this is the kind of thing, and here you at this instant current becomes 0. So, as long as current is conducting any of the thyristors, voltage, you will get a voltage across the load. Then once current becomes 0, then only you can chop, and so you have to chop it when basically chop the voltage when current becomes 0. So, this is the one of the distinction while operating. You cannot turn off the thyristors at your will. Once this current goes 0, then only you will turn it off, and that duration can be extended if you wish, and accordingly things will change. So, thereafter again you have turned it on. So, you again this current again you have chopped it at this point. So, you are blocking this voltage, whatever the voltage part which has been missing, VTH here, and thus the load current will be actually ISS is this basically this source current and plus the thyristors current, that is basically ITR, where this blue one is I load and green one is ISS, and this one, this TR, is essentially the thyristor current. So, there is a distinction of how you trigger if your load is inductive for AC regulator. So, you can have a AC to AC converter single phase. So, you are getting this thyristors, and this is essentially a tap changer which is frequently used in our transformer applications for regulating the load voltages. So, this is the where actually you are getting TR1. So, once you are getting TR1 and a single phase regulator as a static switch, it will work. So, it will having a delay of angle alpha. We assume that it will be delayed by small angle alpha, and generally loads are inductive. So, this will be the profile of the current, and it has been delayed like this. So, you will get this kind of profile of load voltage across the load. So, that is for, and this red one for when actually upper thyristor is gated, and tier when actually red one is for the when lower thyristors is gated. So, your amplitude will come down, same sequence will be followed. Now, this concept can be extended for the 3-phase system. Once you extend it for the 3-phase system, you have a 3-phase 3-wire AC regulator with a balanced resistive load. So, since it is a nothing special here of the, since it is a resistive load, you will get same thing. So, you have to maintain the sequence. Most positive phase should conduct from the and you have to see that most positive phase and the most negative phase of the thyristors. So, this is the same sequence has been followed here. So, what we have seen in case of the converter into the AC to DC application, these are the 3-phase voltages, and these are the these are the phase voltages, these are the line voltages, and you have gated, since the inversion operation, you will actually you will give to the gate Ig1, and it will conduct for the for alpha equal to here it is 120 degree. So, it will be actually given a gate triggering at an angle of 120 degree, and it will be off at this point. Similarly, you will another positive side thyristors, that is Ig3. So, see that this is actually T1 and T4, this is T3 and T6, and this is T5 and T2. So, another positive thyristors will be triggered here. So, another positive thyristors will be triggered actually at an angle of 120 degree. Similarly, this is for the G5 and this is for the G2 and G6, and essentially what voltage you get is basically, if you see that, this is the voltage you will get, and since from upper end only T1 is conducting and from the lower end this voltage is conducting, so you will get this voltage. Since this duration there is no thyristors is conducting, there will be a gap. Thereafter a pause of 120 degree, so there will be no thyristors is conducting and you will get a huge pause of 120 degree. Thereafter again these spikes will come and you will get these voltages. And instead of that, if you change this voltage to 60 degree, a triggering angle at 60 degree, so you trigger it here from the zero crossing of this A and C phase, so essentially this point. So, you can find that corresponding to it, it will conduct. Previously actually G5 was conducting, so you are getting voltage. Here you can see that in these configurations 5 and 6 is conducting, thereafter 6 and 1 is conducting, thereafter 1 and 6 is conducting, thereafter 1 and 2 is conducting, thereafter 1 2 is conducting, but voltage is same, so you will not get any voltage. Similarly, you will get 2 and 3 as conducting same voltage, but actually 2 become more negative than 3 and thus you get a negative voltage and so on. An effective value of ECC will be equal to 0.5 in this configuration. So, this is the way actually by triggering thyristors we can have a AC regulator. So, similarly you can have a 3-phase delta connected AC regulator for balance 3-phase load. Now, again you trigger at an angle 120 degree. So, this is actually IG1, this is for IG2 for a duration of 60 degree, and you will find that basically this is IAB, this is IBC. So, there will be a negative part of it. So, IBC basically this is IBC and this is ICA. So, IA will have this kind of situations, IB will be this kind of situation since it is delta connected. So, you can talk about more about the current. So, there will be a difference between the line voltage, there is no difference between the line voltage and the phase voltage, but there will be a difference between the, these are the line current and these are the phase current for angle 120 degree. So, you get this kind of ripple kind of configuration. So, what happened 3-phase AC regulator is actually we can have a different kind of configuration. This is essentially a delta connected load where current is the consideration, and thereafter you may have some places you have neutral point. So, neutral it is available. So, this is basically 3-phase 4-wire or star connected system with neutral, and you may have a control delta. So, your actually your basic difference is that this point actually connected at this point. So, this is the 2-3 configurations that has to be considered. So, let us see in a comparison table. So, 3-phase AC regulators, rating of the parameter used in the 3-phase AC regulator. Delay angle alpha with 150 degree, the maximum input line current is EAC by root 3 Z, and maximum power dissipation will be the same. So, for the thyristors it will be actually V RWM by VSE. So, it will be around 20% more. I peak will be actually 1.44, that is root 2 times more, and mean AC current of the thyristors it will be 45% and mean RMS current will be basically 70% or 1 by root 2. Delta connected 3 phase AC regulator. So, your minimum line current is basically root 3 AC by Z. So, maximum power dissipation is this. So, you have a thyristors rating will be more and peak current rating will be actually thyristor current rating will be reduced. So, this one is actually preferred. So, again you can see that it is for same delta connected load of the 3 phase system, this value is same, this value is same, this value is same and this value is so. There is no difference of the 3 phase 3 wire AC regulator and 3 phase delta connected load. So, these are essentially same value, and 3 phase 3 wire load for 180 degree you can see that this value of the maximum input current is the same, but here this ratio is reduced. So, you have an advantage, but the peak current ratio will be the same as is higher. So, but mean is same and the thyristor rating is same, and control delta which we have seen here you can find that these values are actually the same of this 180 degree of conduction. So, delta connected 3 phase AC regulator what you get in 180 degree mode of conductions, you get same thing in control delta for 150 degree mode of conduction. So, for this reason control delta sometime is preferred over the delta connected 3 phase normal load. Now, till now what we have actually discussed essentially we have actually controlled the magnitude of the AC system, but that actually essentially it is something like you are applying a reduced voltage to the machines, but with a modern control technique is placed we require to also control the frequency of the regulator or the output. So, for this reason we require a converter which not only change the magnitude of this actually applied voltage, but also the frequency of this applied voltage. And for this reason cycloconverter is a direct frequency changer that converts AC power to one frequency to AC power at another frequency by AC to AC conversion. Cycloconverter are used in high power, high application drives, driving synchronous and the induction motor. They are usually phase controlled and they use thyristor due to their age of natural or the phase commutations. So, let us see. So, this can be actually this frequency can be changed. This is something like universal transformer, where not only the magnitude, but also the frequency of this input and output can be changed. So, we have discussed about dual converter while discussing DC to DC converter. This is one of the example of the essentially a miniature of the cycloconverter, where this you have a this we say that it is a p type converter, and this is basically the inversion operation. You feed this actually the thyristors and ultimately you got an AC load here, and here also you got an AC load. So, here previously we had a DC to DC converter. Here it has to be operated in alpha and it has to be operated 180 degree minus 180 degree minus alpha, but here this load is DC. So, for this reason what happened, you have actually Vm sin omega t, and this side also you got a Vn sin omega t, and you will control in such a way you get a difference frequency by subtracting or adding, and this will be the control circuitry that will be controlling this actually the phases of these two voltages. So, let us take an example. So, this is an example and we assume that load is resistive. So, this is the p type converter when it is on. So, you get this positive voltages and you continue to on for few cycles. So, you get only this kind of waveform. Thereafter, you turn it on the lower converter or the N converter. So, then it will generate the negative portion of the waveform, and thus what you will get? You get a subharmonics. So, you get this actually the amplitude of the voltages. So, this was the this is basically acts as a frequency step down transformer. So, where by chopping basically in this way you are getting a high frequency to low frequency conversion, and this is the way you will get. And if you have a RL kind of load where voltage and current will have a phase lag, then you have to actually turn it on when current through the thyristors, turn it off when current through the thyristors is 0. So, you will get this kind of IS into the system. So, this is the operation with the RL load. So, this is the example of the idealized load voltage and the current waveform with the RL load. So, this is the source voltage, this is the actually output voltage, and this will be the current load, and this part when it is actually negative portion of the current, that will be controlling by the N converter. When both are positive, then it is basically rectifying operation, then it will be contributed by p type converter. Again it will continue, it is continuing in, this will be alpha, then this will be 180 degree minus alpha, because it will operating in a inverting mode. Similarly, here in this case these cycles and these cycles are having a 180 degree minus alpha phase shift, and this will have a basically again if it is alpha, here again it will be having 180 degree minus alpha. This way you will be sequencing, and thus you will be generating this actually high frequency to the low frequency. Now, this can be extended to the 3 level inverters, it can be extended to the 3 phase inverters, and thank you for your attention. This will discussed in our next class. So, this is the combinations of the thyristors that can be used for the 3 phase half wave cycloconverter, and same thing you can extend to the, this is a complex circuit, we have to explanation require time. So, for this reason we are postponing our discussion in our next class. So, this will be the 3 pulse cycloconverter supplying the 3 phase. We shall start from this actually 3 phase cycloconverter in our next class. Thank you for your attention.